Hello friends, welcome to a new Amaze. In today's episode we are going to talk about agent memory. We are going to learn about the long-term memory system, about the short-term memory system, and how to implement both these systems in our agentic backend using LangGraph. So if you're ready, let's begin. Hello guys, so in today's episode we are going to focus on one of the principal components of any agentic design, the memory. The memory can be split into a short-term memory and a long-term memory, all right? And we are going to see the basics of each one of these systems. So let's begin with short-term memory. This is the simplest, and that's the reason why I put it in first place. So you can think of the short-term memory as the chat history. Maybe you have worked with LangChain, with Llama Index, with any of these agentic frameworks in the past, and you are familiar with this chat history abstraction. Okay, this is just a list or a queue that contains all the sequence of exchange of message exchanges between the user and the assistant. In LangGraph, the chat history is stored in the graph state. In fact, if you go to the code and you go into the state, remember that we were creating our philosopher state, the state that we are going to use in our workflow, in our LangGraph workflow. This is something that we saw in the previous video. We are inheriting from the messages state that contains a message property with the list of all the messages exchanged between the user and the assistant. All right, just to give you a quick refresh, remember that in the previous video we implemented this workflow, okay, here in LangGraph Studio. All right, so the chat history, as I was saying, is stored in this messages attribute in the graph state, and what we are going to do in PhiloAgents, both for the short-term memory and for the long-term memory, is to persist this state inside MongoDB. We could choose any other database, but in this case we chose Mongo. And here in this diagram you can see a visual depiction of everything that I've been talking about. So we have this LangGraph workflow right here, and here we have the state that is going to be persisted into the MongoDB database. All right, so it's quite simple. So now let's go into Phaser, into the simulation, to see how this works, okay? All right, so basically the short-term memory allows us to do things like this, okay? So to keep track of the conversation. So for example, hello, I'm Miguel, all right? So I'm just telling my name to Turing, I'm Alan Turing. And if I ask again about my name, Turing, thanks to this short-term memory, is able to remember my name. So do you remember my name? Yes, Miguel, I recall, let us call the Turing test, etc., etc. But you get the point. By using the short-term memory implementation in MongoDB, we are able to persist all of this chat history, all of this sequence of exchanges between the user and the assistant, in this case, Turing. Okay, in fact, let me show you, if we go to, this is Compass, by the way, it's very fancy if you want to explore your MongoDB local instances. If you go to Compass, you will see that, let me rephrase, if you go to PhiloAgents database, you will see that inside there are two collections, the philosopher state checkpoints and the philosopher state writes. These two collections are going to be used by LangGraph to persist the state of the graph. In fact, if you get inside one of them, for example, to checkpoints, you will see references to the thread ID of Turing. That's the PhiloAgent that we have been talking to. So yeah, this is how LangGraph is going to persist and to keep track of the different changes in the LangGraph state, all right? Because of course, when we keep talking to different PhiloAgents and when we progress our conversation with Turing, for example, the state is going to change. And this is how LangGraph is going to keep track of all of these changes, all right? So yeah, this is everything in terms of what I wanted to show you in MongoDB. But right now, I also want to show you how this works in the code, because I think this will make things even clearer. So first of all, let me show you the specific point where this call to MongoDB is going to be done. when we have a conversation with a PhiloAgent. So if you go to the application and conversation service, let me close this for now. You should go to the generate response module, all right? And in here we have this async def get response and the get streaming response. Both of them are valid for this explanation. So let's go, if you want, to the get streaming response. This is the one that is going to be accessed, that is going to be retrieved by the game UI in Phaser. But inside you will see something that we already mentioned in the previous video, that we are using this async MongoDB saver, all right? In fact, this is just a library, a Python library, LangGraph checkpoint MongoDB, that you can install and that you are installing in this project using UV at the beginning of the first video. But yeah, this is the class that we are going to use to define the checkpointer for our LangGraph workflow, okay? This async MongoDB saver. And to do it, you will see that it's very, very simple. I mean, first of all, we are defining the graph builder, okay? Remember that this class is just defining the graph and returning the graph builder. And then we are creating this async with async MongoDB saver, passing different information from the MongoDB instance, this local instance that we are using, and defining the name of both the checkpoint collection name and the rights collection name. That, by the way, remember, were these two, the philosopher state checkpoints and the philosopher state rights. Okay, so then we are, of course, taking this checkpointer and assigning this checkpointer to the checkpointer attribute of the compile method. And just with this line, we are telling LangGraph that we want to store the LangGraph state after each iteration, after each interaction with the graph, right? And that's basically it. Then we are just defining, of course, the thread ID in the configuration to keep track of the different philosopher. Remember that this thread ID is going to be assigned to a philosopher ID so that LangGraph it is not confused between the different philosophers, because we have Turing, we have Socrates, we have many different agents, and we need to keep track of the state of the chat history of each one of these philosophers. And that's the reason why we need this thread ID, all right? After that, we are just defining the streaming logic with graph AStream, and we are returning everything to the FastAPI application. And from the FastAPI application, we are returning everything to the game UI, all right? Great. So just before we go to the long-term memory, which is, I think, much more interesting, let me show you a last example of how the short-term memory works with a very visual example with this Jupyter notebook, because I think that after you understand, after you run the example that I have created here in this Jupyter notebook, everything will be much more clearer to you, right? So let's select the kernel first of all, and yeah, Python 3.11.9. Yeah, so let's start by importing a bunch of stuff here. So I think MongoDB saver, human message from LangChain, create workflow graph. This is the function that I have just shown you that defines the LangGraph workflow. Importing the settings and the philosopher class. Remember that this philosopher class is a domain class that we use to define the different agents. It's an abstraction that wraps the agent logic, right? Perfect. So apart from that, well, let's give this a few more seconds, because it's installing some stuff about OPIC. Okay, perfect. So now this is done, and we can go to the next cell that defines two functions. The first function is the generate response without memory, and the second one is the generate response with memory, which I think it's pretty straightforward to understand what are the goals of the two functions. The first function, the generate response without memory, is going to accept a philosopher class and also the messages, a list of messages, and it's just going to invoke the graph as it is without any kind of checkpointer. Okay, so we are just compiling the graph without any checkpointer, and we are invoking the graph asynchronously with the messages and all the different information that we need for the graph to succeed. Okay, so the philosopher name, philosopher perspective, the style, the context, etc. and as the return object, we are just getting the last message. All right. And for the second function, the generate response with memory, we are passing the same inputs, so the philosopher and the list, but the difference is that we are implementing the checkpointer as we did in the generate response module. Remember that we have just seen that, and yeah, we are defining all the different information from MongoDB, and we are passing the checkpointer to the graph builder compile method. After that, we are just taking the philosopher ID as the thread ID to pass as the config to the graph A invoke, to the asynchronous invoke. In this case, you can see that we are not using the streaming fashion, we are just invoking asynchronously. That's just because I thought it was simpler for this example. Okay, so let's run this cell and define the two functions. And now let's move into the first example, PhiloAgent without short-term memory. And let's see how it goes. So first of all, we need to create the graph builder. All right, graph builder created. And now we are just going to create a test PhiloAgent. This is not an existent PhiloAgent, but now that I was messing around with this example, I thought that it would be really funny to create Andrea Karpathy in some future versions of PhiloAgents. So yeah, the philosopher ID is Andrea Karpathy, the name Andrea Karpathy as well. Perspective, he is the goat of AI and asks you about your proficiency in C and GPU programming, and the style that he is very friendly and engaging, and he is very good at explaining things. Okay, so it's a very realistic depiction of Andrea Karpathy. Perfect, so we have the test philosopher, and now we are going to define just one message, one simple message. That's hello, my name is Miguel. And we are passing this message to good old Karpathy. So generate response without memory in this case, and just let's see the result. So the response of my message is, hi Miguel, I am Andrea Karpathy. I'm excited to chat with you about AI and programming. What's your experience with C and GPU programming? Okay, so that's expected. But now if I try to ask again, do you know my name? See what happens. So I use again the generate response without memory, and surprise, surprise, no, I don't know your name. I'm Andrea Karpathy. Nice to meet you. What brings you here today? So I don't think this caught you by surprise, because that's exactly the goal of this function. But let's see what happens if I add the checkpointer to the graph. So we are defining the same philosopher, Andrea Karpathy, and we are asking the same silly question. Well, not a question, just an affirmation of my name. So, hello, my name is Miguel. Perfect. So now with generate response with memory, we are getting a similar response to the one we received before. So I'm curious, do you have experience with C and GPU programming? But if we ask about my name again, the response is going to change. We just met. You told me your name is Miguel. I am Andrea, by the way. So you see that by using this checkpointer, the async MongoDB saver, of course you could be using a SQLite saver or a DuckDB saver or a Postgres saver, whatever you want, but by storing all of this information, all the state of the graph into disk or into memory, that also works, you are able to keep track of the conversation. You are able to emulate what the chat history class used to do in the past in LangChain. Okay, perfect. So now that you are a ninja in short-term memory, let's move into something more interesting. Let's move into the long-term memory. So why do we need long-term memory, you might be asking? So we are going to use this long-term memory to store relevant information or context about the agent. And by context, I mean life events, biographic information, philosophical ideas about the specific philosopher. We want to ground every response, every philosopher or PhiloAgent response to historical context, to real context. And how are we going to retrieve all of this context? Well, we are going to retrieve this information from the Wikipedia and also from the Stanford Encyclopedia of Philosophy. The process is going to be really simple. First of all, we are going to fetch a lot of information from these two sources. Then we are going to chunk this information, and we are going to use an embedding model to transform each of these chunks into an embedding vector. And then we are storing this embedding vector into MongoDB. All right, MongoDB has a vector search feature that allows you to use MongoDB as a vector database. So that's the reason why we also chose MongoDB, because we thought it was really nice to have the two capabilities, like a regular database and also a vector database, in the same ecosystem. So now I'm going to show you how the long-term memory looks like in the video game simulation. All right, so let's go to a simulation again. And for example, here we have Turing, don't run away, and let's ask about, I don't know, can you give me a description of the Turing test? This is a question in which we are asking about a specific information from the context, from the biography, from the philosophical ideas of Alan Turing. And that's the reason why the agent is going to retrieve some context from Wikipedia and from Stanford Encyclopedia of Philosophy, right? So the Turing test involves a human evaluator conversing with a human and a machine without knowing which is which. If the evaluator can distinguish, the machine passes, right? So all of this information is going to be fetched from MongoDB, all right? So now what I'm going to show you is how this looks like in the code, in the repository. We are going to start by checking the makefile, because the makefile contains a command, create long-term memory, that is going to do all the process for you. It's going to retrieve all the content from Wikipedia and from the Stanford Encyclopedia of Philosophy. It's going to chunk the content, and it's going to store all of this content as embedding vectors inside the vector database, in this case MongoDB vector search. All right, so first of all, let's start by running this command. And as this is going to take some time, I'm going to explain everything that is happening under the hood while this command is running, right? So yeah, I think this is right. So create long-term memory. Yeah, perfect. So yeah, perfect. I think it's running. So now this create long-term memory is calling one function from the tools folder. And the tools folder is right here. Inside, you can find this create long-term memory Python module that implements a CLI application using Click. All right, so this application is going to call the long-term memory creator. And this long-term memory creator is the main class that we are going to use for all this offline population of the MongoDB with the embeddings. We are first of all defining a retriever and also a splitter. But what I want you to focus on is the call method, because it contains the main logic of this class. All right, so to begin with, we are just going to get the instruction generator. And what this function is going to do is to access the extract Wikipedia function and the extract Stanford Encyclopedia of Philosophy. And these extractors, which by the way, are just document loaders from LangChain. One of them is Wikipedia loader. So we had a specific loader for Wikipedia, but we had to implement the Encyclopedia of Philosophy one because there's not such a loader right now in LangChain community. So we had to use the web-based loader, but both the struct Wikipedia, this one right here, and the struct Stanford Encyclopedia of Philosophy are going to download and to extract documents for a single philosopher from or Stanford Encyclopedia of Philosophy or Wikipedia, right? So what is going to happen here is that we are passing the philosophers, this list of all the philosophers in PhiloAgents, to the get instruction generator. In each of the iterations, we are going to access all the relevant docs or the relevant documents that have been retrieved from Wikipedia and from Stanford for a given philosopher, all right? Then for each one of the philosophers, we are going to, first of all, split the documents. And let me show you the splitter that we defined here at the beginning of the class. This splitter is just a recursive character text splitter, as you can see right here. And we are just passing the chunk size as parameter to define the chunk, the size of the chunk that you want to apply. And also we are setting, based on the chunk size, the chunk overlap. As it is a recursive chat character test splitter, it's going to chunk with a specific overlap, right? And we are defining the overlap right here. Okay, so as I was saying, we are using this splitter to split, to chunk all the docs relevant to each one of the philosophers. And we are assigning the result to this chunk docs variable. After that, we are using this deduplication operation, using the duplicate documents function that is going to remove duplicates in the documents, okay? Because you are downloading a lot of things blindly in some sense, and you need some way to remove duplicates, okay? In this case, we are going to remove these duplicates using content similarity. In particular, we are using this min hash algorithm to identify the similar documents, right? You can see the implementation here inside the duplicate documents module. All right, so after we have cleaned the chunk documents, after we have removed all the duplication, it is time to store everything inside MongoDB. And this is done using the retriever class that we created here. By the way, if you remember in the previous video, we were using this retriever and this get hybrid search retriever as well to create the tool that we are going to use in LangGraph. Okay, but that's something that I'm going to show you right now. And yeah, nothing more to add here. So this get retriever just creates and returns the hybrid search retriever that we are just importing from LangGraph. This is something that we didn't implement ourselves. We are just using this class, the MongoDB Atlas hybrid search retriever, that we are importing from the LangChain MongoDB retrievers. Okay, so this is not something that we have implemented, but we saw that the result is quite good. And in the get retriever, we are just going to get an embedding model, and then we are just getting the hybrid search retriever that we are defining here. Okay, this LangChain retriever for MongoDB. All right, so it turns out that all the long-term memory creation has just finished successfully. So now if we go to Compass again, you should see, let me update. Okay, here it is. So inside Philosopher long-term memory, inside this collection, you will see all the different chunks that we have been storing inside MongoDB. Here you have information about Plato, number speaks, relationship between Plato and Pythagoras, Heraclitus, Parmenides. I don't know if you are nerds in philosophy, but this is accurate. And yeah, you will have the same for all the different philosophers, but Plato seems to be the first in the list. But yeah, you will have basically the same. Here you can see all the counter. So yeah, here we have Aristotle, and here we have as well Socrates and Descartes and all the philosophers that are populating our philosopher village. So that's very good. That's great. So now that we have this chunk stored into MongoDB, I can show you how the retriever is going to function. It's going to work in the online phase. Okay, so just as a quick refresher, let me show you here in the graph. Remember that we were implementing a node called the Retrieve Philosopher Context node. If you go to the implementation, remember that we were using this tool node to turn the retriever into a tool to be used in LangGraph. Okay, so if you go to the tools implementation, you can see here that we are just creating the retriever tool out of the retriever, all right, out of the hybrid MongoDB retriever that we have just implemented in, let me check the file, so I think I close it, the MongoDB retriever that we implemented here. Okay, so that's basically the tool that we are going to create using the create retriever tool function from LangChain. And after that, this tool is going to be used by the agent. All right, so whenever the agent decides that it needs to fetch some relevant context, some historical facts, etc., from the MongoDB vector database, then it's going to run, it's going to use this retrieval tool. Okay, perfect. And just before we go, just before this video is over, I just wanted to do the same as we did with the short-term memory, but with the long-term memory. Okay, so in this case, you're going to see how everything works in a very simplified way so that the concept about long-term memory is better understood. Okay, so let's start by importing the documents, the document class from LangChain core, and also a long-term memory retriever that from PhiloAgents application. Okay, perfect. After that, we are just setting the MongoDB URI as we did in the previous notebook, and this is going to point to our local instance. Okay, the one that it's running right now in Docker. By the way, I didn't mention that before, but for everything to work, you need to have your PhiloAgents Docker Compose application running locally. Okay, otherwise nothing is going to work as you might expect. Okay, so yeah, don't forget to start everything. Just remember that you can start the simulation using this infrastructure app, make infrastructure app. This makefile will start everything for you, and you can start testing the Jupyter notebooks or doing whatever you want with this simulation. All right, so yeah, let's keep running. I think, no, this was already run. We are just defining this handy function for printing the different memories. And now we are just going to instantiate the retriever, long-term memory retriever built from settings. All right, now we are going to use the query Socrates for our retriever, and we are going to print the memories. All right, the memories that are basically all the chunks that we are going to receive, that we are going to fetch from the vector database, right? But yeah, it's a very beautiful metaphor. Okay, so let's run the query, and you can see here that there's a memory 1, Aristophanes and other sources or writers of Athenian comedy, and the source seems to be Wikipedia. Okay, the Socrates page in Wikipedia, and here we have the Socratic problem, who was Socrates really, and this is from the Stanford Wikipedia Encyclopedia of Philosophers. So the first chunk, the first memory belonged to Wikipedia, and the second one to Stanford Encyclopedia of Philosophy. And it seems here that the third memory belongs to an entry about Plato in the Stanford Encyclopedia of Philosophy. So yeah, very interesting, but of course they are quite related, so not that surprising. And we can do the same with Turing. So if we use Turing as our query and we use our retriever, then you can see here that there are some information about Turing's time at Sherborne School from Wikipedia, something about the appearance of this paper, Turing's frame foray into a journal of philosophy, okay, something about Turing in Stanford Encyclopedia of Philosophy, and also more information about Turing in Wikipedia. Okay, so about the official Wikipedia page about Alan Turing. Perfect. So yeah, this is how the long-term memory works. And when you start talking with any of these philosophers, with Turing, for example, all of this information from both Wikipedia, from Stanford Encyclopedia of Philosophy, etc., are going to be materialized inside the conversation. And that's the reason why we need it, because we need grounded responses, as I said at the beginning of the video, right? So yeah, now you finally understand how the short-term memory and the long-term memory are really useful for an agentic backend, and how they can improve the interaction of a human with these systems, with these AI systems. On the one hand, we have an agents or AI systems that keep track of the conversation. That's very important, to be honest. And on the other hand, we have systems that are grounded, that are historically accurate, which is very important if you want to build historically accurate simulations like this one. Okay, so this is everything for today. In the next lesson, we are going to learn how to implement all of this agentic backend inside a FastAPI application, and how to use the WebSocket protocol to communicate the FastAPI application and the game UI in Phaser. Okay, so yeah, I hope you have enjoyed this video. Click the like button if you have enjoyed the content. It really helps me. and put me on the comments what you think about these projects, about PhiloAgents. Having said that, have a very nice week, and I'll see you in the next video. Happy coding!